So today we're going to start off with some easier trig function ones. So we're going to start with sine to the fifth of x. And so we're going to take a look at the pattern that we should use anytime we have sine or cosine to a power, if that power is odd. Odd other than 1, obviously. If it's just 1, just integrate it. But if that power is odd and greater than 1, what we are going to want to do is separate off one of the sine x's, and the sine x that we separate off along with the dx is going to become our du. And we're going to turn everything else eventually here all into terms of cosine and let u equal cosine x. And if I had cosine to the fifth, I'd separate off one cosine, turn everything else into sines, and let u equal sine x. So we'll start off with making it sine x times sine squared of x, which then just becomes an integral of sine x times 1 minus cosine squared x squared dx. And then now we can let the substitution u equals cosine x. Substitute everything through. Du will be negative sine x, so we'll throw in some negatives. And this becomes the opposite of the integral of 1 minus u squared squared, or 1 minus 2u squared plus u to the fourth. And then your sine x, or sorry, your negative sine x dx is your du. Everybody good with that? Okay. And so now we've just got a negative, and we've got our integral of this, which is u minus what? 2/3 u cubed plus u to the fifth over 5 plus some constant, which when we separate, not separate, but resubstitute back in with a u equal to cosine, we just, and I can distribute the negative through. This will give us negative cosine x plus 2/3 cosine cubed x minus cosine to the fifth x over 5 plus our constant. Good or no?
Yep.
No, maybe. All right. And so anytime we have an odd power, we could do this. If I had sine to the seventh, we'd do sine and sine squared cubed. And we just end up with a 1 minus cosine squared cubed, which would require some more irritating distributing, but it would work out. And we could do that substitution. And same if it was cosine to the fifth, we'd do cosine times cosine squared squared and turn it into a 1 minus sine squared. Everybody sees that that pattern should work anytime you just have a singular sine or cosine to an odd power.
Yeah.
Great. All right. What about if the power on the sine or the cosine is even, or the even power? That same pattern is not going to work out. Because
power reducing formula?
Yeah,
maybe?
power reducing formula is one option that we can use, and that's what we're going to use here. So in order to power reduce this, we could first, we kind of got two options. One, we could just power reduce it from cosine to the fourth down, but I think I'd rather first write it as just cosine squared x times cosine squared x dx, and then just, power reduce both of those. So what's the power reducing formula for cosine squared? You should know it, but should be 1/2 of 1 plus cosine 2x, and we're going to square all of that because we have two cosine squareds. Good or no? Yeah,
Good.
no, yeah, good. Okay. All right. And so now with the 1/2 squared is a 1/4, so we can pull that all the way out in front. We got 1/4 of the integral of, when we distribute out 1 plus cosine 2x squared, that should become what? 1 plus 2 cosine 2x, and then plus cosine squared 2x dx. And we can start off with making that 1/4. The integral of 1 is x. The integral of 2 cosine 2x is just plus sine 2x. And then what are we going to do with the cosine squared 2x? How are we going to integrate cosine squared 2x? If n is even, we should use the power reducing formula. So how do I use the power reducing formula on cosine squared 2x? Should become still this integral here, right, of 1/2 of 1 plus cosine 4x dx. Good or no?
Good.
Okay. If we distribute the 1/4 through everything, this is going to give us x over 4 plus sine 2x over 4, and then plus 1/8, right? 1/4 times our 1/2 should be a 1/8. And what's the integral of 1 plus cosine 4x? That should be x. And then the integral of cosine 4x ought to be what?
1/4 sine 4x.
1/4 sine 4x. And we got some constant attached out here at the end of all of this junk. And now if we combine our like terms, x over 4 plus x over 8 ought to be what? That's right, 3x over 8 plus our sine 2x over 4 plus now a sine 4x over 32 plus our constant. Good or no?
Yeah, that's good.
All right. So anytime you have sine or cosine to an even power, you can always use the power reducing formulas. What's the power reducing for sine? It's the same as for cosine, except that we get a minus sign in between them. 1 minus cosine 2x instead of 1 plus cosine 2x. But other than that, the same. Good or no?
Where did the 3x over 8 come from? I'm sorry, I don't. Because we have an x over 4, right? And then plus, oh, I see. Why didn't, oh, okay, fine.
Good.
Cool. Yeah.
Cool. Any other questions on that? All right. So if we had sine to the 4th, we'd do the exact same thing, except this would be a minus in between here. And then we deal with it the same way. All right. So what if we have both sine and cosine in it? Well, as long as one of the other of them is odd, then it should become pretty straightforward. Or if both of them are odd. It doesn't matter if they're both odd. As long as one of them is odd, it should be pretty easy. So if one of them is odd, for example, sine cubed times cosine squared, take out the extra one that makes the sine odd. So just make this sine x times sine squared x times cosine squared x dx. And eventually we're going to let u equal cosine x, which will make du negative sine x. So I'm going to want a negative and an integral of a negative sine x. And then this sine squared x is actually going to become 1 minus cosine squared x. And that'll be a cosine squared x dx still. And we should be able to go through and turn everything into u's and du's. So we should have negative integral of, if if u is cosine, this is u squared times 1, so u squared, minus u to the 4th du, which ought to be, if we distribute the negative sign back through there, negative u cubed over 3 plus u to the 5th over 5 plus some constant. And we'll just replace it back through. Cosine to the 5th x over 5 minus cosine to the 3rd x over 3 plus our constant. Easy enough or no?
Yeah.
All right, same thing over here. This time we have the odd on the cosine, so we're just going to turn this into an integral of cosine x, and then a 1 minus sine squared x for the cosine squared that was left, and then a sine to the 4th x dx. And if u is cosine, if u is sine and du is cosine x dx, this just becomes the integral of u to the 4th minus u to the 6th du, with u equal to sine x and du as cosine x dx. Good or no? Any questions or issues on that one?
No.
All right, everybody feels all right. So single trig function, sine or cosine odd should be a u sub. Single trig function power, so with sine or cosine, power is even, power reducing. Both sine and cosine, at least one of them odd, u substitution. Both sine and cosine, both of them even, what do you think we should do? That's right. We should use power reducing. All right, so sine squared should give us 1 minus cosine 2x times a half. And cosine squared x ought to give us 1/2 times 1 plus cosine 2x. And we can take the 1/4 out. And then we can distribute together the 1 minus cosine 2x and the 1 plus cosine 2x to give us 1 minus cosine squared 2x. And then we'll need to do the power reducing formula for that. So what should our power reducing formula give us? If we want to, we can do 1/4 times, if we integrate the 1, it should be x minus the integral of what? If we do power reducing on cosine squared 2x, it should be a 1/2 of 1 plus cosine 4x dx. Good or no?
Yes, good.
Okay, and then should end up giving us x over 4 minus, let's see, this is integral of the 1 is x, and I got a 1/4 times a negative 1/2 times the x. So that's going to be minus x over 8. And then we're going to have minus 1/8 of the integral of cosine 4x, and the integral of cosine 4x ought to be sine 4x over 4 plus our constant. And so what do we end up with? We just get x over 4 minus x over 8, which is x over 8, minus sine 4x over 32 plus our constant. Easy enough?
Don't we need to integrate the x? There's a 1, it's 1 plus cosine 4x.
Yeah, I did that. So I just distributed the 1/4 times the negative 1/2, and then the integral of that 1 was x, so that's the minus x over 8 right here.
Yeah, sorry about that.
No, you're good. Good or no? Everybody okay or not? All right. Now, especially for even powers and when they get a lot higher, it can be exceptionally irritating to have to go through and do this power reducing formula and can cause you to make a lot of mistakes. So what we're going to do here is rather than always rely on power reducing, we're going to develop what is called a reduction formula for the integral of sine to the n of x. And in order to do that, we're going to have to try to integrate this function by parts. So we're going to see what we can do if we integrate this thing by parts, and try to do this as neatly as possible. Switch my laptop around so it's like flat. So you guys can still see the screen, right?
Yes.
Oh, good. All right. So we're going to try to integrate this by parts, and I'm going to give us the beginning part of what we want to do. So we're going to let u equal sine to the n minus 1. Wow, this is not working as well. U is sine to the n minus 1 of x. So if that's what u is, and we're doing this by parts, what should dv be?
Sine.
Should just be sine x, right? dx. Because u times dv needs to be what's inside of here, and sine to the n minus 1 times sine to the 1 should just be sine to the n of it. So what does du then come out to be? Du ought to be, this is u to the n minus 1, right? With u equal to sine x, that's the chain rule. So it should be n minus 1 times sine to the 1 power less, which would be n minus 2, times the derivative of sine x, which is cosine x, dx. And what does v equal? Integral of sine should just be negative cosine, right? Everybody good with u and dv and du and v? Or no?
Yeah, those look good.
Okay. All right. So this integral should be equivalent to then what? Should be u times v. So that'd be negative, I don't know why I wrote an integral sign there. Should be equal to u times v, which is negative cosine x sine to the n minus 1 of x. So u times v minus the integral of v du. And if I'm going to do minus this integral of v du, that's the v is a negative, so I'm going to make that a plus in between instead. So this should become plus the integral of, and in fact, give me a second here, cosine x times this sine to the n minus 2 of x times another cosine x. So cosine squared x times sine to the n minus 2 of x dx. And I've left one thing out, which is this n minus 1 here, which is just a constant. So I'm going to put that out in front. Good or no?
Yes, good.
All right. Wonderful. So is there a way then that I could rewrite the cosine squared in there so that I no longer have a cosine squared in there?
You could do the power reducing formula, or you could do 1 minus sine squared.
The power reducing formula is not going to get rid of a cosine, right? Because
Yeah.
power reducing formula ends up with the cosine still. So let's go with 1 minus sine squared x times sine to the n minus 2 of x dx. And from there, I should be able to distribute the sine to the n minus 2 to all of this. And so that should then give us what? Negative cosine x sine to the n minus 1 of x plus n minus 1 times the integral of, well, if I distribute the sine to the n minus 2 to the 1, that's just going to be sine to the n minus 2, right, of x dx. And then what's the other one? I'm going to make this into two different integrals here. So should be minus, and then we'll still have an n minus 1 out in front, sine to the second times sine to the n minus 2 should just be what?
Sine to the n.
Sine to the n of x dx. And what do we notice here? Now that I've separated that second. It's the same as what we were originally looking at. True? So we should be able to say that all of this crap that I just wrote there is equal to the integral of sine to the n of x dx. Everybody agree there?
Yeah.
Okay, so now let's put it all together here. Let's combine the sine to the n of x dx integrals together. So I have one of them and I have n minus 1 of them on this side. I actually have a negative n minus 1 of them. So if I add n minus 1 of them to this side, n minus 1 of something plus one of those things is how many of them?
N of them.
Would be n of them. So we should end up with negative cosine x sine to the n minus 1 of x plus n minus 1 integrals of sine to the n minus 2 of x dx is equal to n integrals of sine to the n of x dx. And if we just want to know how many, if we want to know what the integral of sine to the n of x is, we just need to divide everything by,
n.
n. Okay, so this should tell us that the integral of sine to the n of x dx is equal to all of this stuff divided by n. So that's negative cosine x sine to the n minus 1 of x over n plus, if I'm dividing this thing by n, I can just divide the constant out in front by n. So plus n minus 1 over n integrals of sine to the n minus 2 of x dx. And this is what we call the reduction formula. Any questions on how we developed that? And so we'll note that this is, it's fairly complicated to develop this formula, but it's actually pretty cool. What happens is, suppose I started with sine to the 10th of x, and I wanted to know the integral of it. Well, the sine to the 10th of x should be negative cosine x times sine to the 9th of x over 10 plus 10 minus 1 over 10, so 9/10 of the integral of sine to the 8th of x. Well, that still leaves me with an integral of sine to the 8th of x. Well, all I have to do is just reapply this reduction formula for sine to the 8th of x, and it'll drop me down to something that is then sine to the 6th, and then it'll drop me down to something that is sine to the 4th. Then I'll do it again, I'll be down to sine to the 2nd. I can do it again to get down to sine to the 0, which is just 1, and just integrate the 1 at the end and be done. So you can just, apply this formula over and over as many times as you need to reduce something down to an easy power to integrate. You can even do it if you wanted to with something like sine to the 5th of x. Apply it down to sine to the 3rd, and then apply it down to sine, and then you can just integrate the sine at the end. Does that make sense or no?
Yeah,
These can be developed for all sorts of different functions. Like you could develop one for cosine or for tangent or for natural log. There's one for natural log. One's for lots of different functions where you can just reduce the powers of these different functions to make the integration a little bit easier. Any issues? Everyone okay? Not okay? Is Shri sending weird things in the chat again? Sure looks like he is. I don't know. I'm worried about whether or not I should click on that. So I know we could do sine to the 6th of x just by using the power reducing, but let's see if we can apply the power reduction formula. So our power reduction formula says this integral should be negative cosine x times sine to the n minus 1 of x over n plus n minus 1, so 5 over n, 5/6, the integral of sine to the 4th of x dx, right, to n minus 2. Everybody good with that as a first step?
Indeed.
Great. And so then our second step will then be to deal with the sine to the 4th of x. So 5/6 times, now it should be negative cosine x times sine to the 3rd x, this time over 4, now plus 3/4 of the integral of sine squared of x dx. And so if we go through and simplify a little as we go, negative cosine x sine to the 5th x over 6, and then that should become minus 5/24 of cosine x sine cubed x. And then we should have a plus 15/24 of the integral of our sine squared x. So we could just integrate our sine squared x, right? Don't need to bother writing out sine squared x. 15/24 times that integral, which is what? Should be negative cosine x times sine to the 1st of x over 2 plus, and then if this is n is 2, that would become 1/2 the integral of sine to the 0, or just 1 dx. So in the end, we should get negative cosine x sine to the 5th x over 6 minus 5 cosine x sine cubed x over 24. 15 over 24 is the same as 5/8, right? And so then that'll become 5/16. So minus 5 cosine x sine x over 16. And then we've got 15/24 times a half again, which is just going to be another 5/16. And the integral of 1 should be plus 5x over 16. Plus your constant. Don't forget your plus of c at the end. be ashamed to go through and do all of that correctly and then forget your plus c and lose a point. Good or no? Any questions?
Should we mention?
What?
Sorry. Should we mention this, like that we're doing the power reduction rule when we're on the AP test?
Yeah, if you were going to use it on the AP test, you should say, yeah, using the reduction formula. I don't care if you do on any of my stuff because I know that I've taught it to you, but yeah, you should at least indicate that you're doing it if it's on the AP test. Chances are you won't need to use it on the AP test because they don't generally give you annoying integrals like this, but you never know. Any other questions on that before we move into some other functions? Move away from sine and cosine and move into tangent and secant. So we are going to take a look at integrating a tangent to a power times secant to a power. And specifically, the best way to do this when the power on the secant is even. So if the power on the secant is even, you always are going to want to separate out a secant squared from everything else. So we're going to rewrite this as tangent to the 6th x times 2 secant squared x's multiplied together. And the reason for that is I know I can convert one of the secant squared x's into terms of tangent, and then I can let u equal tangent, which will allow my secant squared x dx to go away. So we're going to let u equal tangent x with the du equal to secant squared x dx. So this will become the integral of, and we know that secant squared is equal to 1 plus tangent squared, right? So this will be the integral of u to the 6th times 1 plus u squared du. Or an integral of u to the 6th plus u to the 8th du, or u to the 7th over 7 plus u to the 9th over 9 plus a constant. And when we resubstitute the tangent back in, tangent to the 7th x over 7 plus tangent to the 9th x over 9 plus our constant. Good or no?
Groovy.
So anytime the secant power, if you have tangent and secant, anytime the secant power is even, separate off a secant squared and turn everything else into tangents. What if we've got an odd power on the tangent? So I know we have an even power on the secant here also. That's fine. So we could, if we wanted to, with an even power on the secant, we could use this method. We're going to turn it all into tangents. But if the power on the tangent is odd, we can also turn everything into secants and let u equal secant x. So what we will then do is we will separate off a secant x tangent x from everything. So that would be an integral of tangent to the 4th x secant to the 5th x times secant x tangent x dx. And so if we do that, that should allow us to turn the tangent to the 4th into tangent squared squared. And we know that tangent squared is secant squared minus 1. So we have secant squared minus 1 squared times secant to the 5th times secant x tangent x dx. And so hopefully from there we can see that the u sub is u equals secant x and du equals secant x tangent x. So anytime you have an odd power on the tangent, whether the secant is even or odd, you should be able to turn everything into secants if you want to. So secant squared minus 1 squared, I'll give a secant to the 4th to start with, times secant to the 5th is secant to the 9th, or u to the 9th. And then we have a minus 2 secant squared times the secant to the 5th, so minus 2 u to the 7th, and then plus 1, so plus u to the 5th. Good or no? For
Great.
those of you that aren't slowly leaving, apparently people are just slowly leaving class today. This is too boring for some people. So we got u to the 10th over 10 minus, that'll go up to 8, and we'll divide by 8, so that'll be minus u to the 8th over 4, and then plus u to the 6th over 6, plus our constant, or secant to the 10th of x over 10 minus secant to the x, not to the x, secant to the 8th of x over 4 plus secant to the 6th of x over 6 plus our constant. Good or no? Any questions? You guys still there?
Yeah.
All right. We feel okay about that or no? Okay. So if the tangent power is odd, easy enough. If the secant power is even, easy enough. But for any other cases, the chances are you're going to need to know the integral of tangent x or know the integral of secant x. Now I know tangent x is one we should already know. What's the integral of tangent x? We did this one the other day and I said, you should probably memorize this.
Negative natural log, absolute value of cosine x. Yeah, plus c.
Yeah, so that one we should already know, and we can do that pretty easily with a u sub, making this sine over cosine with u equal to cosine. But what about integral of secant x? I don't think we've done that one before. That one requires a little bit of a trick. So in order to integrate secant x, what we're going to do is we're going to multiply this secant x by secant x plus tangent x over secant x plus tangent x. And this looks a lot more complicated and like a bigger pain to deal with now that I've done this. But the good news is we should be able to then just simplify this out using a u substitution by letting u equal secant x plus tangent x. So if u is secant x plus tangent x, what is du equal to?
Secant x tangent x plus secant squared of x.
Dx, right? Yep. And so if we look at this, this just becomes an integral of, well, the denominator is u, and secant times secant plus tangent would be secant squared plus secant tangent, wouldn't it? Which is exactly what the du is. So this just becomes the integral of du over u, which is natural log absolute value u plus your constant, or natural log absolute value secant x plus tangent x plus your constant. Good or no? So this integral, the integral of secant x, is equal to the natural log of the absolute value of secant x plus tangent x plus a constant. This is another integral you're going to want to memorize. So for those people that left early, they're not going to know that. Very sad. You will know that. Memorize the integral of secant x is natural log absolute value secant plus tangent. Good or no?
like I understand.
You feel like you understand? You said you do feel like you understand?
I do.
Wonderful. And anybody else besides Noah?
Yes.
Ah, 2 people. All right, good. 2 out of the 32 of you that have decided to stay. Great. All right, let's see if we can apply some of these a little bit. Let's find the integral of tangent cubed x. Any thoughts on what we might do with that?
Do it by, oh wait, no, never mind.
So yeah, that doesn't give us one of those, it doesn't give us that tangent was even or secant had an odd power, right? This is just tangent has an odd power. So we're gonna have to find some little trick to deal with this. Any thoughts? All right, great idea. Let's rewrite it as tangent x times tangent squared x dx, because I at least know how to do something with tangent squared, right? Tangent squared could be the same as secant squared minus 1, couldn't it? So oftentimes use the trig functions to rearrange, and what does that give us here in this integral now? It's an integral of tangent x secant squared x dx minus an integral of tangent x dx, doesn't it?
That is what it gives us.
Yeah, and so how can I integrate tangent x secant squared x? I can let u equal tangent, and du will be secant squared, and that will give us an integral of u du, and then this one will become minus negative natural log absolute value cosine, so plus natural log absolute value cosine x, and the integral of u ought to be u squared over 2 plus the natural log of the absolute value of the cosine x, and we got some constant attached to this, and we should then just end up with tangent squared x over 2 plus natural log absolute value cosine x plus your constant. Good or no?
Splendid.
All right. Cool. We got just a couple more problems we're going to do, and then we will be done for the day. So let's take a look at this. Tangent squared secant x. And take a minute and think about what might you want to do with this one. Does it meet the criteria for the power on tangent is odd, or the power on secant is even?
No.
No, it doesn't. So we're going to have to find some other way to deal with this. So is there any piece of this that can already be rewritten as something else?
Tangent squared x.
Tangent squared x, right? We could rewrite tangent squared x as secant squared x minus 1 times secant x and dx. And what could I do with that then, you think? Any thoughts on what to do with that?
Distribute.
Sure. Let's do an integral of secant cubed x minus secant x dx. Do I know how to do any part of that or no? what's the integral of secant x? Natural log absolute value secant x plus tangent x plus some constant. True?
This is true.
Okay. So then all that's left is for us to do what?
Integrate secant cubed x.
Yeah, figure out this secant cube. So how are we going to do that? Any thoughts?
Can you split it into secant x and then the secant squared x would become 1 plus tangent squared x? Or 1
Okay.
minus?
Okay,
1
so
minus 1 plus, I don't remember.
so you want to write it as an integral of secant x times, and since it's secant squared, that'll be 1 plus tangent squared x. Is that right? Like that? Is that a yes or no?
Oh, yes, sorry.
Okay.
Yeah.
All right, good. Okay, so that's one thing that we could make an attempt at here. Now, if I were to do that, I would need to then distribute this secant x through. So this will give me the integral of secant x dx plus the integral of secant x tangent squared x dx. And I liked where you were going with this because it seemed reasonable based on what we've been doing. But we now have a problem. So this whole thing was originally the integral of tangent squared secant x, right? That's what we originally had. And we've now got that that's equal to the integral of secant plus the thing that I started with minus this natural log. And so effectively what I've got over here is, what's the integral of secant? It's natural log secant plus tangent. And those will cancel out. And if I subtract this one over, those will cancel out, and I just end up with some constant equals some other constant, which seems to be an issue, doesn't it?
Yeah.
Yeah. So it was a good idea because it made sense. It was what we did to start the problem, right? So why not continue and use that same process again? Well, this is why not, because sometimes when you try and go through and do this, you end up getting 0 equals 0 or constant equals constant or something like that. So we've gotten rid of all of this. Let's try something else. Any other thoughts? What else have we done so far that is new with integration in the last 2 days?
By parts?
By parts. All right. Let's give by parts a try. So let's let u equal, well, let's see, if it's secant cubed, u could either be secant cubed, or it could be secant squared, or it could be secant, right? Those are really the 3 choices. And dv could be also any of those. Which one of those is really easy to integrate? It has a really nice, clean integral. Secant cubed, secant squared, or secant? Secant squared does, right? So let's make dv secant squared x dx, which would make u secant x, which would make du secant x tangent x dx, and v just tangent x. Everybody good with that? So I'm going to say that my original integral, the integral of tangent squared x secant x dx, should be equal to u times v, which is secant x tangent x, minus the integral of v du, which is secant x tangent squared x dx, and then minus this natural log absolute value secant x plus tangent x that we had from before. And I could put that plus C1 there if I wanted to, but I guess I will. Why not? And now what can we do with this?
Set it equal to the original.
Yeah, set that over there equal to the original. So that should give us two integrals of tangent squared x secant x dx is equal to secant x tangent x minus natural log absolute value secant x plus tangent x plus some constant, or that the integral of tangent squared x secant x dx should be all of that over 2. So secant x tangent x minus natural log absolute value secant x plus tangent x all over 2 plus some new constant. So fairly involved process there. But we'll see that knowing the integral of secant and knowing the integral of tangent is going to be fairly important for some of these tangent secant trig functions that we need to integrate. Good or no?
Yeah.
Cool. All right. We're going to do one more quick little thing here, of which I would not expect you to see any of these integrals on the AP test, but it's, you know, possible that you could. We're going to look at the sine of mx cosine of nx, or sine mx sine nx, or cosine mx cosine nx. So like, you know, something like sine 2x cosine 3x, where we've got a product of two different trig functions, sine and cosine, or sine and sine, or cosine and cosine, within our single integral with different arguments in the sine of the cosine. So not sine 2x cosine 2x, but sine 2x cosine 3x, different values. So if you ever happen to see something like this that you need to integrate, the easiest way to do it is by using the product to sum identities. And they should be on your paper that I have posted in Google Drive. It's you know, it's got all the, it's like 4 pages of trig stuff. It's not ones that I told you need to memorize, because you probably don't need to memorize them, but it's good to at least be familiar with them somewhere down the road when you need to integrate something like this. So I'm going to hope that I know these still off the top of my head, but I'm sure you're all pulling up the sheet so that you can tell me if I do this incorrectly. Oh, good. So I believe if we have, what's that? Did somebody say
I was
something?
just affirming.
All right, you're gonna let me know if I have forgotten my product to sum identities. All right, so this integral, I know they all come with a 1/2 in the front, so this should be 1/2 the integral, and I believe sine times cosine is sine of adding them together, so sine of 5x, and then plus sine of subtracting them. Does that look right according to the paper you guys have in front of you?
Yeah.
Good. All right. So then that's 1/2 the integral of sine 5x. Using the even odd identity, sine of negative x is just the same as minus sine x. So we've got this, which should then become the integral of sine of 5x should be negative 1/5 cosine 5x. So that'll become a negative 1/10 cosine 5x. And then the integral of our sine, negative sine x, should become a plus cosine x. So that'll be plus 1/2 cosine x plus our constant. Good or no? Any questions on that one?
That makes sense.
All right, the next one, I know that's also got a 1/2. I believe the sine ones both come to be cosine ones. And I think it's subtraction first. So 1/2 cosine negative x. And I believe it's minus in between cosine of adding them together. Does that look right according to the sheet you have?
Yep.
Cool. And we know that cosine is an even function, so that cosine negative x can just become 1/2 the integral of cosine x minus cosine 7x dx. And if we integrate that, integral of cosine is just sine, so we're going to end up with 1/2 sine x, and then minus 1/14 once we distribute the 1/2 through, sine 7x plus our constant. Good or no? Once you get them separated out into an addition, they're pretty easy integrals, right? Yeah, definitely. All right. And what about this last one? I believe it's 1/2 the integral of cosine of the addition of them. Not that it would matter because I think it's cosine of the subtraction of them. So you could do that in any order, really. Does that look right?
Yeah.
All right. And so if we integrate that, that's going to be a 1/7 sine x and a 1/3 sine, or sorry, 1/7 sine 7x and a 1/3 sine 3x. And if we distribute the 1/2 through, we should get 1/14 sine 7x plus 1/6 sine 3x plus our constant. Good or no?
Yes.
Wonderful. That is where we will end up stopping today. Any questions on anything we've done today?